mapping of hydration in lunar pyroclastic deposits, and the implications for lunar volcanic process. Where's it?
Actually, there are none yet.
No.
Oops.
All right, we might need a hand up here. Oh, it's up there. It's just not mirroring.
It's interesting.
There we go. Give me 2 seconds.
Okay. So this map shows our mapped hydration overlay on the LRock WAC image at remote border. I'm going to present a case study at this area, and more details will come in coming slides. As you may know, we are in the process of quantifying lunar surface hydration with the newly thermocorrected M-cube data, as Jim just introduced. So as shown in this image, this is a global mosaic of half key aspect parameter, which is linearly correlated with the absolute water content. So from this map, we can see the lunar surface hydration is dominantly controlled by latitude. The higher latitude, the higher hydration. And based on our lab experiments, we can tell the purple region is around 500 ppm hydration. If you go to the green to cyan region, it may have like 2000 ppm hydration. And also, if you look at the low latitude, at north 30 degree to south 30 degree, you can see there is no or very weak hydration except these pyroclastic deposits pointed by these cyan arrows. Now here's a zoom-in image. From this image, we can tell most pyroclastic deposits marked by these yellow circles show highly hydrated compared with the background. Because these highly hydrated spots are not associated with any craters, we propose these hydration are from lunar interior. I'm going to provide evidence for this hypothesis. So the question for this study are to answer these questions: how these hydration are retained in pyroclastic deposits over geological time scale, and which factors control the spatial variation of hydration in individual pyroclastic deposits, such as volcanic glass abundance or water content in the glass. And last, we want to understand what the water content of pyroclastic deposits tell us about volcanic processes and volatile in magma source. We can compare our estimated hydration with those derived from pyroclastic in-place model as just introduced by Jim, and also lunar sample data. So to understand the hydration retention, we use a hydration diffusion model as shown in this equation 1. And previous lab studies show that the hydration diffusion coefficient is temperature dependent. So we need a thermal diffusion model to get a lunar subsurface temperature as shown in equation 2. And then we use a neural network model to quantify lunar surface volcanic glasses to compare with our mapped hydration directly. The neural network model is a statistics model trained and validated with the lunar soil characterization consortium dataset. We also compare our estimated hydration with the hydration derived from 2 models. The first one is the pyroclastic in-placement model presented by Wilson and Hyde in this year's RPIC. Jim mentioned it in his talk. I'm not going to detail in this equation, but you can look at the papers. Now the second is from the mass conservation model. I feel essentially the same model, but it's a different way. As shown in this equation, the left side is the total mass of pyroclastic deposits in place on lunar surface, and the right side is the total mass of melt in the magmatic form in a deck. From this equation, we can get the melt fraction F, and 1 minus F will be the gas fraction. So plugging the F into this equation, we can calculate the volatile concentration. And what I want you to know is here in this equation, the pyroclast deposit depth D is required. We can derive this value from the air rock neck image based on the crater diameter to depth ratio. So this is our post-emplacement diffusion model for hydration. And the left plot shows the lunar subsurface temperature profile at a depth from 0 to 0.8 meters at a latitude 0 degree. And the solid line is the maximum temperature at each depth. And the dot line is the mean temperature at each depth. And the dashed line is the minimum temperature at each depth. After we get the temperature data, we can calculate the hydration diffusion coefficient and plug the coefficient into the hydration diffusion model. We can calculate the diffusion profile for water, as shown in this red figure. But the difference is I'm showing just from 0 to 1 millimeter depth. And I calculate the 3-time period diffusion. The blue line is after 1 million year diffusion. The red line is after 1 billion year diffusion. And the black line is after 3 billion year diffusion. From this plot, we can tell at an optical depth around less than 400 micron. This is just for glass. So the optical depth is maybe deeper. And we expect at least 60 to 90% of the hydration can be retained through 1 to 3 billion years exposure diffusion process. However, the porosity, permeability, and surface adsorption, those factors will affect on this diffusion process, but has not been taken into account. We will integrate these factors into our model in future studies. Now let's look at the comparison between the hydration map with the mapped glass abundance. Again, we are showing a case study at Rimaboda. So the left plot shows our hydration map at Rimaboda, while the left plot shows the mapped volcanic glass. They are color-coded in the same way, so spatially you can see they match very well with each other. Now then we directly compare them pixel by pixel. The y-axis is the volcanic glass, the x-axis is the hydration level. We can see they show a very good linear trend. This may tell us the volcanic glass is the dominant factor controlling the bulk hydration level on lunar pyroclastic deposits. Then we compare our estimated hydration with those derived from the pyroclastic emplacement model at Rimaboda. And to play this model, we needed to know the maximum range the pyroclasts were ejected. So we can measure directly from this map is around 73 kilometer. And we use the model as exactly the same as Jim described just now, and plug those numbers into this equation. We can calculate the total volatile required to emplace those pyroclastic deposits is 29,000 ppm. And based on this year's presentation by Wiesel et al. In this year's RPIC, they said they found from Apollo samples only around 1% of those volatiles may likely hydration. So the hydration may be 290 ppm. After around 1 to 3 billion years diffusion, around 170 to 260 ppm left. While our estimated hydration at this area is around 210 ppm, so fall within the range very well. And again, as I said before, we do use the mass conservation model to derive the total volatile. We needed to get the depth of the pyroclastic deposits. We are showing a case study again at Rimaboda and using the neck image to count the crater based on the crater diameter depth ratio to get the thickness. So as shown in this yellow box is the neck image cover region. And we classify craters in this region into 3 groups. Group 1, you can see here with the black halo and clear ejectory. We group these craters as penetrating through the pyroclastic deposits. And craters without any bright halo, but with sharp boundaries, you can see clearly as shown here. We group these craters as the ones not penetrating through the layer. While the craters, if the craters are highly eroded, we are not counting these ones because we don't know whether these craters happened before or after the Pyroclastic deposits. And also, we're following these craters, crateries. We choose smooth regions, and we also avoid the ejected blanket of large craters. So this plot shows the summary of our crater counting. The black bars shows the craters did not penetrate through the deposits, while the red bars shows craters penetrate through the deposits. This is the frequency, the distribution, the population, and this is the crater excavation depth. So from this figure, we can tell craters with excavation depth less than 4 meters generally do not penetrate through the layer. And craters with excavation depths larger than 10 generally all penetrate through the layer. So we are confident to say that the layer must be within like 4 to 10 meters, but with 2 sigma, we can tell the thickness is around 4 to 8 meters. Now then we can play the mass conservation model to derive the total volatiles. But to perform that model, we need 2 parameters. The first one is the total area of the Pyroclastic deposits. We can measure from the map directly, as shown here. And also, we need the deck length. The deck length can be constrained by these highly hydrated regions. And we do like a lot of measurements and do average calculation. It's around like 60 kilometers. And the area is 15,000 kilometers. And plug in all these parameters into the equation, we can calculate the melt fraction is around 28 to 49%. And then we can calculate the total volatile concentration is around 14,000 to 33,000 ppm. And if we still assume only 1% of these are water, it will be like 140 to 340 ppm. Our estimation, again, is 210, so fall within the range very well. So to conclude, our post-emplacement diffusion model shows that most of the hydration can be retained in Pyroclastic deposits through geological time scale. And in future work, we will integrate the porosity, permeability, and surface out-of-option, those factors into account. Second, the hydration abundance in Pyroclastic deposits show a very good linear correlation with volcanic glass abundance. This may tell us this hydration may come from the lunar interior along with the glasses. And also, the glass abundance is the dominant factor control the bulk hydration level in lunar Pyroclastic deposits. Third, our estimated hydration values are consistent very well with those derived from Pyroclastic emplacement models. And this may tell us the water content measured at the surface can be related to the magnetic process and the volatile content of source magmas. That's it. Thanks. I'll be ready to take questions.
Nice talk, ShuaI.
Hi, Clive.
I just wondered if you'd looked at whether or not the hydration that you're seeing also correlates with optical maturity, and maybe you're seeing solar wind implantation in these deposits. Have you checked that?
Yeah, it's correlated with the maturity very well, but the latitude is a dominant controlling factor. If it goes higher latitude, you can see the correlation very well. I gave a presentation last year at PSC. I showed that results.
Yeah, well, that was a long time ago for me.
Yeah.
So you do see a correlation with optical maturity in these things?
With the maturity?
Yes, with maturity.
Yes.
Okay.
Yes, very strong at a high latitude.
Jeff Taylor, University of Hawaii. You may have just answered this question, but this number of 210-ish that you get for the abundance is a lot higher than measured in orange glasses and green glasses. And so maybe is this consistent then with what you're really seeing is the space weathering contribution, not the magmatic contribution?
That's possible, but for the green glass and the yellow glass we have, they are far away from very large pyroclastic deposits. So I don't think that they are representative enough. Yeah.
Last question here.
Okay, thanks. Carl Hibbs, APL. Just understand the diffusion that you're modeling. Is that internal diffusion of hydrogen within the grain, or is it water diffusion around the grain?
Oh,
is
it's
it
in the
okay if I
grain.
ask 2 questions?
It's in the green.
It's in the grain, yeah.
Yes.
Thank you. Also, Darby Dyer did some work, I think last year or something, looking at the effect of composition on the depth of the OH band. And there's a pretty strong dependency there with an orthostatic terrain, which has a deeper band, also having a stronger absorption constant. So bands look stronger in highland material naturally than they would in Maury material.
Yeah, that's if you just look at the band depth directly, that's true. But we do conversion from reflectance to single scattering albedo and convert a single scattering albedo to aspect. So that can remove the effects from like material difference and multiple scattering.
But isn't single scattering albedo infinitely tied to the absorption constant?
Maybe you cannot remove clear totally, but you can remove most. There is a paper published by my advisor, Ralph Millikan, in 2005. You can check his paper. He did a lot of lab experiments to show that after the conversion, you can remove the effects.
I heard that. Yeah. Good paper.
Thanks.
Okay. Well, let's end there and let everyone run off to lunch.